I still remember the first time I looked up and saw something that didn't belong to our solar system. Not a planet, not a star, but a wanderer from another star system, 3I/ATLAS. Tonight, I want to take you on that journey with me. Come closer. Let me tell you about the visitor that changed everything. It was late November 2024 when I first heard the whispers. I wasn't in some grand observatory perched on a mountaintop, telescope pointed at the heavens. No, I was sitting in front of my laptop, coffee going cold beside me, scrolling through the astronomical telegram service the way some people scroll through social media. It's a habit I picked up years ago, checking for supernovae, gamma ray bursts, anything that might be breaking the cosmic routine. And then I saw it. A single line in a preliminary report from the ATLAS survey, Asteroid Terrestrial Impact Last Alert System. The report was terse, technical, fast-moving object detected, hyperbolic trajectory, further observations required. Hyperbolic trajectory. Those two words made my heart skip. See, most objects in our solar system follow elliptical orbits, closed loops around the sun, bound by gravity, prisoners of our star's embrace. But a hyperbolic trajectory, that's an open curve. That means the object is moving so fast that the sun's gravity can't hold it. It's just passing through. It means the object came from somewhere else. I leaned closer to the screen, my pulse quickening. Could this be real? After Oumuamua in 2017 and 2I/Borisov in 2019, we'd been waiting. The entire astronomical community had been waiting for the next interstellar visitor, wondering if we'd ever see one again in our lifetimes. And now, here it was, announced not with fanfare, but with a quiet technical dispatch in the middle of the night. I pulled up the coordinates, cross-referencing them with sky charts. The object was in the northern sky, moving through the constellation Corona Borealis. Not particularly bright yet, magnitude 12 or so, invisible to the naked eye, barely a whisper even to decent backyard telescopes. But it was there, and it was moving, fast. The preliminary velocity estimate put it at around 55 kilometers per second relative to the Sun. To put that in perspective, Earth orbits at about 30 kilometers per second. This thing was outrunning us, and it wasn't slowing down. In fact, as I dug deeper into the orbital calculations being posted by astronomers around the world, I realized it was speeding up as it approached the Sun, exactly as you'd expect from something on a hyperbolic trajectory, gravity accelerating it inward, then flinging it back out like a cosmic slingshot. I sat back in my chair, staring at the screen. Somewhere out there, beyond the edge of our solar system, beyond the Kuiper belt and the Oort cloud, beyond the influence of our sun, this object had been traveling. For how long? Thousands of years? Millions? It had crossed the vast, cold emptiness between the stars, a journey so incomprehensibly long that light itself takes years to make the trip. And somehow, by chance or fate or the blind mechanics of gravity, its path had intersected ours. Within hours, the amateur astronomy community was buzzing, forums lit up, Twitter threads spiraled, everyone wanted confirmation. Was this really it? Was this our third interstellar visitor? The professionals moved quickly. Observatories around the world began slewing their telescopes toward Corona Borealis. Hubble Space Telescope time was requested on an emergency basis. The European Southern Observatory's Very Large Telescope in Chile pivoted its mirrors. Even the James Webb Space Telescope, still the crown jewel of modern astronomy, was being considered for follow-up observations. And then the confirmation came. It wasn't an asteroid, it was a comet. The Hubble images arrived first, and I remember the moment I saw them. There, against the black backdrop of space, was a soft, diffuse glow. Not the sharp point of light you'd expect from a distant star or asteroid, but something fuzzy, something alive. A coma. The comet had a coma, a cloud of gas and dust surrounding its nucleus, evaporating under the sun's warmth even though it was still far out, well beyond Mars' orbit. This wasn't the inert, rocky silence of Oumuamua. This was a comet in full display, announcing its presence with a halo of light nearly 400,000 kilometers across. Two Earths could fit side by side inside that glowing envelope, and the color, oh the color. Spectroscopic analysis revealed a pale green tint, the signature of cyanogen and diatomic carbon molecules fluorescing in the sunlight. It's the same eerie glow you sometimes see in comets from our own solar system, but knowing this came from elsewhere made it feel different, alien, beautiful in a way that made my chest ache. I stayed up all night reading the reports as they poured in, orbital refinements, brightness measurements, compositional analysis. Every new piece of data felt like unwrapping a gift from the universe. The designation came through official channels, 3I/Atlas. The 3I meant it was the third interstellar object ever identified, after 1I/Oumuamua and 2I/Borisov. The Atlas credited the survey that found it first, simple, clinical, but to me, it was so much more. I thought about the journey it had made. Somewhere, orbiting some distant star we might not even know the name of, this comet was born, perhaps in the debris disk of a young stellar system, condensed from ice and rock and organic molecules in the freezing outer reaches. Maybe it orbited peacefully for millions of years, a frozen world in the dark, and then something happened. Maybe a close encounter with a giant planet, a Jupiter-sized world whose gravity flung the comet outward with enough velocity to escape its star's pull entirely. Maybe a passing star disturbed the system, sending icy bodies careening in all directions. Or perhaps a catastrophic collision shattered a larger body, and this was one of the fragments cast into the void. Whatever the cause, 3I/Atlas began its journey into interstellar space, alone, silent, crossing distances so vast that even traveling at tens of thousands of kilometers per hour, it would take millennia to traverse the gulf between stars. And then, by pure chance, it entered our solar system. The discovery of 3I/Atlas wasn't just a scientific event, it was a reminder that the universe is far larger and stranger than we can truly comprehend, that our solar system isn't isolated, sealed off from the rest of the galaxy, that matter moves between the stars, carrying with it the chemistry and history of distant worlds. I finished my coffee, cold as it was, and kept reading, because I knew this was just the beginning. In the days following the discovery, I couldn't stop comparing 3I/Atlas to our previous interstellar visitors. It became almost obsessive, pulling up old data files, rewatching video presentations, reading papers I'd bookmarked years ago. Let me take you back to October 2017. That's when Oumuamua tumbled into our awareness. I remember the confusion, the excitement, the sheer strangeness of it all. Oumuamua was unlike anything we'd seen before, cigar-shaped or maybe pancake-flat depending on which models you believed, tumbling end over end through space at a dizzying rate. No coma, no tail, just a dark reddish object that reflected about as much light as dirty ice or organic-rich rock. It accelerated as it left the solar system in a way that couldn't be explained by gravity alone, leading to wild speculation. Some scientists proposed outgassing, jets of sublimating material too faint to see but strong enough to give the object a tiny push. Others, more boldly, suggested it might be an artificial object, a light sail from another civilization. But the most frustrating thing about Oumuamua? We barely had time to study it. By the time we realized what it was already leaving. Then came 2I/Borisov in August 2019, discovered by amateur astronomer Gennady Borisov using a telescope he built himself. This interstellar visitor was refreshingly normal. It looked like a comet. It acted like a comet. It had a beautiful, obvious coma and a developing tail. It outgassed water vapor and carbon monoxide in ratios we recognized from solar system comets. And crucially, we had time. Borisov was detected earlier in its passage, giving astronomers months to train every available instrument on it. We measured its nucleus size, somewhere between 0.5 kilometer and 1 kilometer across. We analyzed its composition. We even watched it fragment slightly as it rounded the sun. But 3I/Atlas was something else entirely. First, there was the sheer scale of it. That coma, 400,000 kilometers across, was enormous even by comet standards. The sun's diameter is about 1.4 million kilometers. This comet's glowing envelope was nearly a third of that width. If you could somehow see it with your naked eye from up close, it would dominate your entire field of view, a ghostly sphere of green light stretching from horizon to horizon. Then there was the velocity. At 55 kilometers per second relative to the Sun, 3I/Atlas was moving faster than Borisov, though not quite as fast as Oumuamua. But speed isn't everything. It's the trajectory that matters, and 3I/Atlas had a beautifully clear hyperbolic orbit, the mathematical proof of its interstellar origins. I spent an entire evening playing with orbital simulation software, plugging in the parameters as they were refined by professional astronomers. Watching the path traced across my screen was mesmerizing. The comet approached from the direction of the constellation Ursa Major, the Big Dipper, diving down toward the Sun at a steep angle. At perihelion, its closest approach on October 14, 2024, it would still be about 230 million kilometers from the Sun, roughly 1.5 times Earth's orbital distance. But here's what made 3I/Atlas truly special to me. Its composition. The spectroscopic data coming in from Hubble and ground-based telescopes revealed something fascinating. The green glow came from cyanogen and diatomic carbon molecules, common in comets. But there were also hints of other compounds, water vapor certainly, carbon monoxide, possibly ammonia. The exact ratios were still being worked out, but preliminary analysis suggested a composition remarkably similar to some solar system comets, particularly those from the Oort cloud. This was significant. It meant that whatever stellar system 3I/Atlas came from, its chemistry wasn't wildly alien. The basic building blocks, water ice, organic molecules, carbon compounds, seemed universal, at least in this small sample. Yet there were anomalies. The comet's brightness fluctuated in ways that weren't entirely explained by a simple rotating nucleus. Some observations showed rapid changes in brightness over just a few hours, hinting at either an irregular shape, active jets firing from specific locations, or possibly even fragmentation. This instability intrigued me because it echoed something we'd seen with Borisov. Was 3I/Atlas structurally weak, held together loosely like a rubble pile, or did it have a harder, more coherent nucleus with a fragile outer crust that was now peeling away? One researcher I followed on social media speculated, half joking, half serious, that maybe 3I/Atlas wasn't a pure comet at all. Maybe it was something hybrid, a captured object that had spent time in another planetary system's inner regions, getting baked and processed before being ejected. I loved that speculation, not because it was necessarily true, but because it reminded me how much we still don't know. Every interstellar object is a unique mystery, a one-of-a-kind ambassador from a place we'll likely never visit. And unlike Oumuamua, we had time. Unlike Borisov, this one was bigger, brighter, easier to study. We had a chance, maybe our best chance yet, to truly understand an interstellar visitor before it disappeared forever. Where do you come from? That's the question that haunted me every time I looked at the latest images of 3I/Atlas, not in a casual conversational way, but as a genuine mystery that kept me awake at night. Because here's the thing about interstellar objects, their origins are almost impossible to pin down with certainty. They don't come with return addresses, they don't carry markers identifying their home systems. All we have is their trajectory through our solar system, their velocity, and their composition, clues we can use to build educated guesses, but rarely definitive answers. I started with the trajectory data. When you rewind 3I/Atlas's path, projecting it backward through space, you can get a rough idea of which direction it came from. The comet appeared to originate from somewhere in the general direction of Ursa Major, the Big Dipper, but general direction is doing a lot of work in that sentence. Space is three-dimensional, and interstellar distances are vast beyond comprehension. Even if we knew the exact vector 3I/Atlas followed, tracing it back to a specific star system is nearly impossible because of gravitational perturbations. As the comet traveled through the galaxy, it would have been nudged by the gravity of passing stars, giant molecular clouds, even the galaxy's overall gravitational field. over hundreds of thousands or millions of years, those tiny nudges add up. Still, astronomers tried. I watched as research teams ran simulations, modeling the comet's possible journey backward through the Milky Way. They factored in the galaxy's rotation, the distribution of nearby stars, the known velocities of stellar systems. There were no obvious candidates. No single star system jumped out as the clear origin point. Instead, the simulations produced a cone of probability, a region of space where 3I/Atlas might have originated, spanning dozens of light years and containing hundreds of potential stellar systems. So I turned to what we could know, the chemistry. The composition of 3I/Atlas told a story, even if we couldn't read all the chapters. The presence of water ice, carbon monoxide, cyanogen, and organic molecules suggested it formed in the cold outer regions of a planetary system, similar to our own Oort cloud or Kuiper belt. These are the deep freeze zones, far from a star's warmth, where volatiles like water and methane can condense into ice and accumulate over millions of years. This is where comets are born. In the early days of a planetary system, when planets are still forming and the disk of gas and dust is thick and chaotic, gravitational interactions are violent. Protoplanets migrate inward and outward, their gravity flinging smaller bodies in all directions. Some of those bodies get tossed into the outer reaches, where they settle into stable orbits and remain frozen for eons. 3I/Atlas was likely one of those bodies, born in the outer edges of another star's planetary system, shaped by the same physics that shaped our own comets. And then something changed. This is where speculation becomes almost poetic, because we can imagine so many scenarios. Maybe a gas giant planet migrated through the system, its gravity destabilizing the orbits of countless icy bodies. Maybe a rogue star passed nearby, its gravity stirring the outer reaches of the system. Maybe the system experienced a close encounter with another stellar system in a dense star cluster. Or, and this is the scenario that gives me chills, maybe 3I/Atlas was ejected during a catastrophic event, a collision between planets, a supernova shockwave from a nearby stellar death, the violent disruption of an entire planetary system. But here's what really captured my imagination: the age. How old was this comet? When did it begin its journey? If 3I/Atlas traveled at its current velocity and came from a star system just 50 light-years away, the journey would have taken roughly 250,000 years. That's longer than modern humans have existed. The comet would have been launched into space around the time our ancestors were still living in Africa, still learning to use fire. But if it came from farther away, 100 light-years, 200, 500, the journey could have taken 1,000,000 years or more, longer than our entire species has walked the Earth. And during all that time, it was alone, floating through the interstellar medium, the thin soup of gas and dust between the stars, encountering nothing but hydrogen atoms and cosmic rays. The temperature would have been just a few degrees above absolute zero, no sunlight to warm it, no planets to perturb its orbit, just silence and cold and motion. Until now, I tried to imagine what it would be like to be that comet, to drift for eons in the dark, then suddenly feel warmth again, to approach a new star, different from the one you were born under, and begin to awaken. Let me tell you what it's actually like to see an interstellar comet. I drove out to a dark sky site about 2 hours from the city on the night of October 21st, 2024. That was the date astronomers had circled on their calendars, when 3I/Atlas would be at its optimal viewing position for observers in the Northern Hemisphere. The drive was worth it. No moon that night, just the Milky Way spilling across the sky like spilled milk on black velvet. I set up my telescope, a modest 8-inch Dobsonian, nothing fancy but perfectly adequate, and let my eyes adjust to the darkness. In the city, your pupils never fully dilate, but out here, after 20 minutes, the sky transformed. Stars I'd never noticed before emerged. The universe opened up. I pointed the telescope toward Corona Borealis, a small, semicircular constellation that most people never bother to learn. But on this night, it held something precious. Finding 3I/Atlas required patience. I used my phone app to get the exact coordinates. Comets don't shine like planets or stars. They don't announce themselves. And then I saw it, not as a sharp point, but as a soft smudge of light, a subtle, diffuse glow against the background stars. If I looked directly at it, it almost disappeared. But when I used averted vision, looking slightly to the side, it bloomed into view, a pale greenish haze, roughly circular with no sharp edges. The coma looked small from this distance, maybe a few arc minutes across, but I knew the truth. That tiny smudge represented a cloud of gas and dust, hundreds of thousands of kilometers wide. I sat there for a long time, just watching it. Every photon entering my eye had been emitted by molecules of cyanogen and carbon, excited by sunlight, fluorescing in that characteristic green glow. Those molecules were boiling off the surface of an object that had traveled across interstellar space. But this wasn't just my experience. All over the world, people were doing the same thing. I'd seen the posts on astronomy forums. Someone in Japan captured a long exposure image showing a faint hint of tail structure. An observer in Spain managed to catch it near a bright star. Amateur astronomers in Chile reported slightly better views. And then there were the professional observations. The Hubble Space Telescope had been granted emergency time. The images it captured were extraordinary. In visible light, the coma showed that characteristic green glow, but with detail my telescope could never resolve. Hubble could see structure within the coma, subtle variations in brightness, hints of jets emanating from the nucleus. The James Webb Space Telescope also turned its infrared eyes toward 3I/Atlas, and what it revealed was fascinating. The thermal signature of the nucleus itself, buried beneath the coma. Early reports suggested the nucleus was warmer than expected on the sunward side, but perhaps my favorite observations came from spectroscopy. Spectra don't make pretty pictures, they're graphs. But to a trained eye, they're beautiful. Each spike is a fingerprint, identifying a particular chemical species. The spectra of 3I/Atlas told a chemical story. Water vapor, carbon monoxide, cyanogen, diatomic carbon, possibly ammonia. Some researchers thought they detected hints of methanol. Others reported possible traces of formaldehyde. If confirmed, these would be significant. Organic molecules, the building blocks of life, traveling between star systems. Around 2 a.m., I noticed something. The comet had moved, not just the apparent motion from Earth's rotation, but actual motion against the background stars. Over 3 hours, it had shifted position, traveling its hyperbolic path at 55 kilometers per second. That movement was so slow from our perspective, so subtle, that it required patience to notice. But it was there, real, measurable. This was our window, our chance. But seeing 3I/Atlas wasn't enough for me. I needed to understand what it meant. Because every interstellar object is more than just a visitor. It's a sample, a piece of physical evidence from another planetary system, delivered to our doorstep without us having to travel light years to collect it. Could 3I/Atlas carry clues about the formation of planets around other stars? Absolutely. The ratio of different ices tells us about the temperature gradient in its birth system. The presence of certain minerals in the dust could reveal whether its parent system had rocky planets, asteroid belts, processes similar to our own. But the question that gripped me most was this: could it carry organic molecules? Not just simple ones like methanol or formaldehyde, but complex organics, amino acids perhaps, or the precursors to them. We know comets in our own solar system carry such molecules. The Rosetta mission to Comet 67P detected glycine, the simplest amino acid, right there in the coma. The Stardust mission returned samples from Comet Wild 2 that contained organic compounds more complex than anything we'd expected. If 3I/Atlas carried similar chemistry, it would tell us something profound, that the organic ingredients of life aren't unique to our solar system, that wherever planets form, wherever ices condense in the cold outer regions, this chemistry emerges. Some scientists went even further with their speculation. What if interstellar comets like this are actually vectors for spreading organic chemistry between star systems? Panspermia has always seemed far-fetched when talking about microbial spores surviving the radiation of space, but complex organic molecules are harder. Frozen in cometary ice, shielded from radiation, they could survive the journey. I didn't know if I believed it, but I loved that 3I/Atlas made the question feel urgent again. And then there was the question I kept returning to: how many more are out there? If we've detected 3 interstellar objects in just 7 years, how many have we missed? How many passed through the solar system before we had the technology to spot them? The calculations suggested the galaxy might be teeming with such wanderers. Billions, trillions, a vast, invisible sea of exiled worlds carrying stories we'll never read. The discovery of 3I/Atlas didn't just light up telescopes, it lit up the world. I saw it first in the forums I frequented. Within hours of the announcement, conversations exploded, people sharing coordinates, comparing observations, posting their first images. There was a palpable electricity in those discussions. Someone in Australia posted at 3 a.m, "Just saw it. Can't believe I'm looking at something from another star system." A researcher in Germany responded, confirming strong CN emission. This is the real deal. This is what I love about astronomy. It's one of the few human endeavors where nationality, politics, and personal differences dissolve completely. We were all just observers, witnesses to something larger than ourselves. The professional community was equally energized. I followed several astronomers on social media. One tweeted at 2 a.m, "Just submitted a proposal for JWST, fingers crossed." The urgency was real. Everyone knew this was a limited time opportunity. Unlike solar system comets that we can track for years, 3I/Atlas would fade from view within months. But it wasn't just astronomers who were captivated. I saw news articles appearing in mainstream media. Some of the coverage was oversimplified, but anything that got people looking up thinking about the cosmos, that was a win. My favorite response came from educators. I saw a high school physics teacher post about taking their entire class outside to observe it. Most of them had never looked through a telescope before. Watching their faces when they realized that faint smudge had traveled from another star, priceless. Kids asked questions adults had forgotten to ask. How long will it take to get to the next star? Could we catch up to it with a rocket? The questions were asked with genuine curiosity, the kind that drives all of science. Artists responded too. I saw paintings inspired by the comet. Musicians composed pieces titled after it. Poets wrote verses about interstellar wanderers and cosmic loneliness. There was something deeply human about all of this. The need to create, to interpret, to make meaning from a natural phenomenon. 3I/Atlas reminded us that we're not separate from the universe, we're part of it. Matter flows between star systems, chemistry is exchanged, and every interstellar visitor is a reminder of that connection. Sometimes, in the middle of observing, I have to step back from the eyepiece and just breathe. I'm standing on a rocky planet, third from a middle-aged yellow star, in the outer spiral arm of a galaxy containing hundreds of billions of other stars. That planet is spinning at about 1,600 kilometers per hour. It's also hurtling around the sun at 107,000 kilometers per hour, and the entire solar system is racing through the galaxy at roughly 720,000 kilometers per hour. In the midst of all that motion, there's a comet, and somehow, against all odds, our paths crossed. The improbability of this encounter is staggering. Space is vast, unimaginably, incomprehensibly vast, and 3I/Atlas crossed that void. It traveled through the interstellar medium, that near-perfect vacuum where you might find a single hydrogen atom per cubic centimeter. What are the odds that an interstellar object would pass close enough to the sun to become visible during the exact century when humanity has telescopes capable of detecting it? Before we had telescopes, how many interstellar visitors passed through? Hundreds, thousands, comets from other stars that came and went without witness. This is what 3I/Atlas taught me. Perspective. We're not the center of the universe. We're observers, conscious matter that has organized itself into a form capable of asking questions about its origins. We're temporary, both as individuals and as a species, but the galaxy will continue. Stars will keep forming in nebulae, planets will continue to coalesce from protoplanetary disks, and comets will still be ejected from young systems, and yet that doesn't make our observations meaningless. If anything, it makes them more precious. We exist in this narrow window of time when we can witness these events, when we can understand what we're seeing. The universe doesn't owe us this opportunity, but here we are, conscious and curious. We're part of a universe that has organized itself into structures capable of contemplating their own existence. We're the cosmos made conscious, looking back at itself. Standing under that dark sky, I felt both infinitesimally small and profoundly connected. November 7th, 2024. I knew this would be my last good look at 3I/Atlas. The comet had faded considerably since October, now magnitude 13, hovering at my telescope's detection edge. I drove back to the same dark site. The sky was perfect, cold, clear, moonless, but this time felt different, a sense of ending. I found it barely visible, even with averted vision, just the faintest smudge, a ghostly memory of the vibrant coma it had displayed weeks earlier. This is what goodbye looks like in astronomy, not dramatic, not explosive, just a slow fade. I sat with it for over an hour, knowing that each moment might be my last clear view. By next week, it would be too faint. By December, beyond reach of all but the largest professional telescopes. Then 3I/Atlas would continue its journey in silence, crossing the orbit of Neptune, entering the vast empty space beyond the Kuiper belt, eventually leaving the sun's gravitational influence entirely. The coma would collapse, the sublimation would stop, the comet would freeze again. It would travel for millennia, perhaps millions of years, before encountering another star. Maybe it would pass close enough to warm again, to be witnessed by other observers, or maybe it would drift forever alone. "Safe travels," I whispered, knowing the comet couldn't hear me. But it felt necessary. 3I/Atlas had given us so much in its brief visit. Data about interstellar chemistry, evidence that our solar system isn't isolated, a reminder of the dynamic, ever-changing nature of the galaxy, and perhaps most importantly, it had given us wonder. I took one last photograph. The image was terrible, grainy, barely showing anything, but I knew what it captured. Then I packed up my telescope and drove home. I would check the professional observations for weeks afterward. The last confirmed observation came in mid-November, a faint infrared signature, barely distinguishable from background noise. And then, silence. The comet that had traveled across the stars, that had visited our solar system during the brief window when humanity could appreciate it, had returned to the void. Never to come back, never to be seen again. But somewhere in the data we collected, 3I/Atlas lived on. We had captured a piece of its story. Perhaps centuries from now, someone will revisit those observations and learn something we missed. That's the gift of interstellar visitors. They remind us the universe is larger and stranger than we imagine, that we're part of a cosmic ecosystem where matter flows between stars. I looked up at the sky one last time. Somewhere up there, invisible now, 3I/Atlas was moving, still traveling, still carrying its ancient ices toward whatever future awaited it. I was grateful for the brief moment our paths crossed, grateful for the questions it raised, grateful for the wonder it sparked. Farewell, wanderer. May your journey be long and may the stars be kind. Maybe one day a comet from our sun will travel to another star, carrying whispers of us. Our own Oort cloud has sent countless icy bodies into the galaxy over billions of years. Right now, somewhere dozens of light years away, perhaps another civilization observes one of ours, asking the same questions we asked about 3I/Atlas. The exchange goes both ways. We're not just recipients of interstellar visitors, but senders too. Our solar system contributes to this galactic mixing, this slow exchange of matter and chemistry across the stars. 3I/Atlas reminded me that we live in a connected cosmos. that the boundaries we imagine between stellar systems are permeable, that matter, chemistry, maybe even the seeds of life, travel between worlds on journeys lasting longer than civilizations. And for a few brief months, we got to witness one of those journeys, to study it, to wonder about it, to feel connected to something ancient and vast. The comet is gone now, receding into the darkness between stars, but it left something behind, not just data, but perspective, a reminder of our place in the cosmic story. I still look up at the night sky and think about it, about the wanderer that crossed the stars and for a moment let us see it, about the countless others out there making similar journeys we'll never witness, and I'm grateful to live in a time when we can detect such visitors, grateful for the technology that lets us study them, grateful for the human curiosity that drives us to ask questions about our origins, our place, our cosmic neighborhood. 3i/Atlas is gone, but the wonder it sparked remains, and perhaps that's the real gift, not just the data collected, but the reminder that we're part of something extraordinary, something ancient, something vast, something beautiful. The universe is filled with wanderers crossing the void between stars, carrying stories from distant systems to our doorstep. All we have to do is look up,